So this is where we left off in the previous video for the D-Ambridge paradox, and now we'll be discussing the lift force, the drag force. So in a nutshell, lift force is the force which is perpendicular to the fluid velocity, and the drag force is the force which is in the direction of the fluid velocity. Suppose this is the fluid velocity, free stream velocity. Lift force could be perpendicular to any direction, either this or this or this, and the drag force will be in the direction of the parallel to the direction of the fluid motion. Now consider a case of a general cylinder, not a circular cylinder. Suppose this is the general cylinder. Let us take an element of length dl. Now if there is a free stream velocity, and we are ignoring viscous effects because we are dealing with potential flows, and if we are dealing with the potential flows, then viscous effects are ignored, so the only force that is being applied on this body is the pressure force. Suppose at this point the pressure is P, then the force will be in this direction. Zoom it a little bit. This is PL, this is pressure force. Suppose the pressure makes an angle theta with horizontal, and this will also be theta since it is normal. This is dx, dy. So force along the horizontal direction, the elemental force along the horizontal direction is pressure times dy. Consider the force to be the force per unit width. So in the unit width, we get the horizontal force is this. This is the drag force per unit length, and dfd equals pressure force dx times 1 equals to dfl, lift force per unit length. Now as we have net force as dfd in the complex plane is dfd minus, sorry, this is plus, this is dfd dfl, but we'll try to find out dfd minus iota dfl. No need to apply vector sign, and that is equal to minus p dy minus iota e dx, and This would be minus iota p px, and this would be plus minus iota dy could be written as iota p dz star, where dz star is the conjugate of dz. Now to find the resultant of the forces, we have to take closed integral around the boundary of this region D, which is partial D. So it will be partial D dfd minus iota dfl, and it will be dfd minus iota f is equals to x minus iota dy. And now we have to find p, since it's a variables rule is Bernoulli's theorem. For a particular streamline, so between the points infinity and the point A, to this point of interest, so it would be p infinity plus half rho infinity square plus p plus half rho v square, where v is the velocity, which is u plus iota v. So we would get p infinity plus half rho u infinity square plus p plus half. Since v is also a complex quantity, you can write it as v times v star, where v square is the magnitude of v square. Now it could be written as p plus half rho u infinity square minus half rho u plus iota v u minus iota v equals to 0. Now it is p, and we get fd minus iota fl equals, let's see where we left off. Yeah. So we'd get iota, then rho by 2 u plus iota v u minus iota v, and dz star This will be written as minus iota close integral p dz star and would get minus p infinity minus p infinity square together with the dz star. Since the closed integral of a constant is always zero, so you get iota rho by 2 closed integral u plus iota v u minus iota v dz star. Now it is simplified further. Dx minus iota dy. Now what we can do, let us do some particular manipulations as follows. Multiply the two highlighted terms. Would get u plus u dx minus u iota u dy plus v dy, then plus iota v dx and we would get u dx plus v dy minus iota u dx minus v u dy minus v dx. Since, as we have proved in the earlier lecture, that the contour of the body is itself a streamline with the value of the stream function equals to 0. So these points, the x and y, the ordered pairs, lie on the streamlines of the contour of this region D, and with the definition of the stream function as u equals to d psi over dy and b equals to minus d psi over dx. So we get u dy as d psi and v dx as d psi, and it would be added and it would be partial d psi, 2 times partial d psi, but d psi is not changing along the contour. So since it's constant along the contour, that's our definition of a streamline. The stream function is constant over the contour, so we get this term as 0 and we'll be just remaining with u dx plus v dy. Since we could do further manipulations as this minus could be removed with a plus sign because the interior of the bracket parenthesis is always 0. So it could be written as u minus iota v times dz So our result would be iota rho over 2 u minus iota v u minus iota v times dx plus iota dy, and we get rho equal to, this is nothing but the complex velocity, that is the differentiation of v z square times dz. This is known as the Blasius force theorem, where this could also be written as f of z, or we have earlier mentioned that w of z. This is the complex velocity. Also, this can be solved using the residue theorem, and it's a kind of very simple theorem, as we have the residue theorem as closed integral f c dc as 2 pi I times the sum of the residues. This is the residue theorem, where fz can be expressed as a Lorentz series, just like a Taylor series for real valued functions. We have a Lorentz series for complex functions. It is c minus 2 times z square plus c minus 1 z c0 c1 z c2 z square and so on. Now we are dealing with flow past a circular cylinder without circulation. So our complex potential phi has only the terms of, the first term was uniform velocity and the second term was a couplet. So it could be written as z plus 1 by z, a type of this kind of potential flow. And if we have to find the complex velocity, it would be v dash z equals 1 minus 1 over z square. Now let us understand the physical interpretation of the constants in the Lorentz series. In all the practical applications, we'll be concerning about these four terms, mainly these three terms and these three terms in pairs and triplets and so on. So this term represents the velocity, free stream velocity, or velocity at infinity. C minus 1 represents the circulation, as we'll be dealing in our next lecture, of a flow past a circular cylinder with circulation, and this represents the flux. This is an important term. Of course, this is also an important term, as it will be necessary to deal the flow across an airfoil, the famous Gupta-Zoroastrian theorem. Jaworski theorem. These are the part of our subsequent lectures, and we'll be seeing that why airplanes fly, ships sail, etc. The aerodynamic phenomena is observed. So let us concentrate on this our simple case. Since P of z is given by this relation, so we have we know that in our simple case there is no circulation, so this can't be a residue, and we have this uniform velocity, so this will contribute. But let's see the integration of the square of this function. We'll get a type of 1 plus 1 over z to the power 4 minus 2 over z squared dz. Since the closed integral of constant is 0, and for the z to the power 4 we'll be integrating, and for the z square, since it represents the flux, so the flux from the contour of this body would always be 0, since there is a doublet concentrated inside. So this would also be 0. This can also be proved using Green's theorem or Stokes theorem. So getting into this term now, let us substitute as out to the power 4 e to the power iota 4 theta dz. Since we are integrating over the contour of radius r, so r is a constant here, and we get to the power iota theta times iota d theta, and we get 1 by r cube iota goes into e to the power minus 3 iota theta d theta. It would always be 0. So we would get, after comparing the lift force 0 and the drag force 0, this is the main part of our lecture, that which is not consistent with the practical observations. Since the lift force is 0, we can understand because of the symmetry, the flow symmetry about the real axis, so it can't be generated in one direction, so the net lift is 0. But if you observe the drag force is not 0 always. This is known as D'Amber's paradox, and that we can't ignore viscous effect to its full extent as 0. There is a boundary layer separation after which we could ignore that, but before that, along just along the contours of the cylinder, we can't ignore that. This was all that we are dealing with.